No. Yeah, I mean, I basically thought about you guys. It's completely fine for me to give the talk, but if I speak in another language here that no one understands, well, anyways. So this, well, maybe I should also use this some of my 40 minutes to thank the organizers. It was really great to be here, and I hope my talk won't ruin this for you guys. It will be about matrix product representation of locality preserving unitaries. It's with Sujit and Fang, who were graduate students when we did this work. Now Sujit is a postdoc in Washington, and with Xie Chan. And I should also insist that you guys should also look at this work, because they appeared about the same time, and basically the main results are the same, but the way that we prove is actually different. Right. So yes. So somehow I put this matrix product representation in the center, and it has really been useful in the past. People use this as ansatz states for pure states, and they showed that physically relevant states like ground states or low energy eigenstates of local Hamiltonians, gaps or gapless local Hamiltonians, have efficient representations in terms of them. And then people, they went on and they actually gave a classification of gap phases. People also use this as an ansatz for mixed states, like for thermal states or for sense matrices. And even they try to, we have used this to explain physical phenomena like topological order by using matrix product operators as virtual symmetries. So it's been used a lot in order to classify mostly the states in 1 and 2D, but no one has actually asked the question of how about unitary operations, right? So we, instead of states, now we are interested about unitary operations. So since I should not assume that everyone is actually familiar with the notation, let's first introduce a graphical notation. So what we try to do, we are given a quantum state psi on n parties. And we write this, let's say, in computational basis from I1 to IN. Each index goes from 1 to small d. And these coefficients that gives us the description of the states, which is linear superposition of these basis states. We say that we write down these coefficients as a product of matrices, or as a product of tensors. So this the basic constructive element of these kind of states is a three-leg tensor. So whenever two lines intersect, you should understand that there is a tensor sitting there. In this case, at this vertex of 3 legs, there's a three-leg tensor A, and the coefficients of this three-leg tensor is denoted by AI alpha beta. So when you fix this alpha, beta, and I computation, you get some numbers here. And this gives you the description of the local tensor. And this notation means that so you put all these tensors on the vertices. You have n of these. And whenever there's an open leg, this should tell you that you have an open index. But whenever there's a closed index, it means that you contract this index, the right index of this tensor with the left index of this tensor. And this is why we have matrix multiplication here. And in this formula, I assumed periodic boundary conditions, which means that this leg is contracted with this leg. And throughout the whole talk, I will assume periodic boundary conditions. So you can describe any state in this form, but you want to use as little bond dimension as possible. So the dimension of this vector space, which we call virtual Hilbert space or virtual vector space, let's call it big T. We don't want this really big, and ideally we don't want it to scale with the system size. You can also play the same game in 2 dimensions. Instead of using 3-leg tensors, you need to use more than 3-leg tensors. For example, you have square lattice. You have a state on this square lattice. And then you try to express this state in terms of a contraction of, in this case, in this picture, 5-leg tensors. One is reserved for the physical degree of freedom, and the other 4 is reserved for the virtual degrees of freedoms. And this leg attached to this leg means they are contracted. So you have to contract these indices. Sorry? So you can think about this state as entangled states. So first you take a product state. Each vertex you have 4 spins. One is here, one is here, one is here, one is here. And this one is maximally entangled with this one, let's say. This one is maximally entangled with this one, with the other spin next to in the neighboring spin. So you can also express, well, the same expression. You can understand it as projecting or applying a linear map only on the 4 spins on these vertices if they are maximally entangled. You get the same description. Yeah, this name is reserved for any dimension. It's not like only 2D. Yeah, this I got it from another presentations. We are not into the meta. So yeah, and then yeah, why is this physically relevant, right? So you can, it's imaginable that it's not so surprising that some physically relevant states have efficient MPS descriptions, but why there should be a guarantee that we can actually express them as MPS? Well, a physicsy way of understanding is using Euclidean path integrals. I guess this slide is also not the best slide for this audience, but anyways, the aim is actually to find the ground state of a given Hamiltonian. Say we have a Hamiltonian, local Hamiltonian, and let's assume it's actually gapped. So there's a gap between the ground state energy and the first excited state. So now imagine that we apply e to the minus ht. So we try to understand this e to the minus ht. If you look at the spectrum of e to the minus h, the ground state of h, and let's assume that it's actually 0. So the ground state, the norm of the ground state basically stays the same. But after applying e to the minus h to any other excited state, it gets contracted. So it's smaller and smaller. And if we apply this e to the minus h many, many, many times, what you get at the output will be very close to the ground state. Of course, I'm glossing over a lot of details, but this is mostly true for gapped systems and with some assumptions in the spectrum. So if h is gapped, this object with relatively small t behaves as an approximate ground state projector. I mean, this is actually not really true, but in some cases you can have constant depth, so you can achieve this goal with constant depth. It's not really true, but yeah, let's say that it's true for some physical systems. And now what you do is that you actually compress all these tensors into one tensor, like this. Then you say that, okay, at the output we have ground state. Of course, there should be an overlap, when we introduce product state here, when we input the product state, there should be at least some high overlap between this state and the real ground state, so that this actually should this can actually work. Okay. Yeah. So why did I show this? There's another reason that I showed this. It's because, well, we had to introduce some concepts, right? So you can express this ground state with these fine-grained local tensors, but some universal properties of these states actually start to appear when you block these local tensors. We basically declare that your new tensor is not anymore, your new local tensor is not anymore this three-leg tensor, but it's this times this times this, and maybe many more. You will still have two virtual bonds, like here and maybe here, but you will have many physical indices. This is sometimes called coarse graining. And for generic MPS states, after you do this, you actually get some universal properties of the states and of the Hamiltonian. And we reach this limit, when we block after finitely many times, we generically reach this. We call this fixed point. Right. Okay, so So basically, people looked at, try to understand ground state properties using this matrix product state representation. So one can see what we are doing as, instead of having e to the minus ht, we want to understand e to the minus iht, which is real-time evolution. So matrix product unitaries may be useful if we understand the structure of matrix product unitaries, they may be useful as an answer to real-time evolution. And as it happened for the matrix product states, which people use to classify 1D gapped quantum phases, maybe we can also classify unitaries up to some local equivalence relation. And it will happen that the equivalence relation that will come out of this result is finite depth local unitaries, as it was the case for the classification of the gapped phases. We will also be able to describe and classify quantum cellular automata. Basically, we will show that what we did turns out to be the same as what David, what Gross, Nesme, Vogtsa, and Werner did 9 years ago. They classified quantum cellular automata. That how matrix product unitaries are actually related to quantum cellular automata. So it's been done 15 years ago then. Okay. Yeah. And it's also interesting for other type of physical systems. So this is very analogous to something called symmetric product topological order. There are some physical systems which are trivial in the bulk, but something interesting happens on the boundary. And we will, in the next slide, we will see that some non-trivial matrix product unitaries actually appear at the boundary of trivial bulk evolution, trivial bulk time evolution. So let's see, let's observe this. We are interested in the following particular finite depth local unitary in a 2D system. So first of all, we have boundaries. So we have a square lattice. At every side, we have some spin degree of freedom. And the time evolution is described as follows. So first, you exchange these two particles, basically in this direction. You swap these particles. And you do it in this direction. Then you do it in this direction. Then you do it in this. So what happens to a particle? It goes here, it goes here, it goes here, and it comes back to its original position. This is what happens in the bulk. But of course, if you try to understand what happens to this spin, for example, it goes here, and then it goes here. Then it jumps here, then it jumps back here. So instead of coming back to its own its initial position, it actually flows on the boundary. So there's a flow in this direction on this boundary, and there's a flow in this. So this is basically a translation boundary. So in the bulk, the time evolution is trivial. It's just identity. But in the boundary, it's a translation. And it will turn out to be the boundary unitary, which are translations. You are not able to express this as a finite depth local unitary. If you want to realize this purely in one dimensions. This immediately already follows from the paper by David and Gross, Vox, Werner. Right. I hope everyone is motivated enough at this point. Why we should study unitary matrix product operators. And this is the flow of the talk. So first we will go back in time and we'll go forward. We will first show that locality preserving unitaries can be expressed as finite bond dimension matrix product unitary operators. And then by assuming only unitarity for MPUOs, we will prove some fixed point equations, which we call separation, isometry, and pulling through. And using these fixed point conditions, we will show that every MPUO is locality preserving. And later, we will also define an index that you can derive locally from the local MPO. And then we will show that this is actually equivalent to the G and VW index. And G and VW is the first names that. Right. So this is a system that people call Floquet systems, because your time evolution is periodic, right? So you do these swaps periodically. This is a different phase than just applying identity on all spins. And these phases are classified by the transport on the boundary. Because in the bulk, it's completely indistinguishable from just applying identity. But on the boundary, you have a transport. And these transports, they can be expressed as MPOs. And you can show that it's indexed by a different number than just identity. So if we are able to classify MPOs, it will help us classify these kind of time evolutions in 2D. These also preserve locality. Yeah, what do I mean? It maps a local operator to a local operator. Or +2. So it increases the range, the support increases, but yeah. Yeah, exactly. Yeah. Okay, so first let's show this. Yeah, it's going to be very easy thanks to these guys. They show that any locality preserving 1D unitary can be expressed as finitely many composition. By composition here we mean multiplication. So you can multiply operators, or you can take tensor products of translations and finite depth unitary circuits. Translations has finite bond dimension MPO representation. For example, translating everything to right is this operator, and the local MPO is basically copying this virtual leg to output, and copying input to the right. So it has a finite bond dimension MPO representation. Finite depth unitaries, so this is a depth 1 unitary, depth 1 local unitary. What you basically do is that you choose your MPO as this part of the operator, the right part of this unitary operator, and the left part of this unitary operator. So you basically get the MPO representation. Finite. Yeah, so you could also choose it like this. But later, yes. So later we will, because you actually want to stack this, right? You want to compose this finite unitary with another one. So if you look at the problem at this, and if you try to compute the index that we define, it will compute here trivially. That's right. That's correct. This is right. Yes, that's right. Yeah. And to be completely general, for the analysis later, we pick it in this way. Right, so thanks to them, every locality preserving unitary has at least one metric product operator representation, because we just compose these MPUOs and define a new local MPUO, we get the representation of a given locality preserving unitary. Okay, this part is done. Now I can. That's the easiest part. Now it's going to get a little bit painful. So now we want to go this way. We only want to assume unitarity for matrix product operators, and we want to see what's the structure of them. So here's the setting. We are given a 4-leg tensor. These are the physical degrees of freedoms, and these are the virtual degrees of freedoms. And when you contract these local tensors in this way, this is now an operator from n spins, I1 to In, to n spins, J1 to Jn. And also, I always assume that there is periodic boundary conditions, so this leg is actually contracted with this leg always. And the condition that we impose is that we want this operator to be unitary for all system sizes greater than some constant C. So this, yeah. We actually want both of them to be unitary, but in the result, we only use one of them. So we can actually use the same result for isometrics. Yeah. So yeah, this is the property that we require for all n greater than some constant C. And here the trick is, well, we have to use the same local tensor M for all system sizes. So we require this property for all system sizes for the same local MPO that we use. There's no a priori reason for this. Well, first, this is the thing that we can understand. Otherwise, we wouldn't be able to understand the structure of this M. Yeah, it's correct. That's what I say. Before some constant system size, it may not be unitary. This also happened? Yes. Right. There's actually, we also understand this setting. These MPUOs, they are not locality preserving. That's what we found. Yeah. It comes from this periodic MPS. Yeah. Well, but this is the setting that we are going to understand. Yeah. Okay, so we want to understand. Well, ideally, we want to understand how M looks like, but we are only able to understand what this guy looks like, what M dagger looks like. So this is a 6-leg tensor. This leg is contracted. This is the input. This is the output physical leg. These are the virtual legs. And what do? We basically apply invertible matrices on these legs by not changing the unitary operator O. So we apply x minus 1s so that this whole operator doesn't change, but we still modify the structure of this T. And what we do it is we see this operator as a state. We upgrade this, well, one of them is bra. So this bra to a cat. So we say that this is actually a state. And if you look at it, this whole tensor network state, when you upgrade all these inputs, all these bras to cats, it becomes product state. So it's a very simple state. And we general form of how local tensors look like by using the steps in the canonical form of MPS, and we obtain general form of this T tensor. Right. There's a huge gap in this slide. So what we do is the following. First, we calculate the transfer matrix of this AJK, which is AJK and AJK dagger. These physical indices are they're contracted, and we calculate the right eigenvector of this. So it may be full rank, or it may not be full rank. If it's not full rank, well, we know that it's a positive matrix because this is a CP map. We basically apply a projector on onto its support. So basically, we apply PV1 and PV1 perp. And if you impose the fact that these guys are, this tensor that we apply here, like x1/2, x to the minus 1/2, by using their positivity, you can actually prove that after modifying these virtual degrees of freedoms, these are the only surviving parts. So either we will have PV1, so we will be in the support of this, this positive fixed point, or we will be in identity and P1 perp. So there won't be any P1 perp, PV1 perp, PV1 term. Yeah, so just believe me on this fact. And then we do this. We do it from right, we do it from left, we do it from right, we do it until eventually we will get full rank positive matrices as the fixed point of this transfer matrix. Well, A dagger. And here, this is the general form that we get after applying these decompositions. Yeah, I think I have a picture here. So this is actually how it looks. First, we actually restrict our tensor to this block, to this big block. But one term is missing, and it's basically this column. So this column is completely zero. This column can have some elements. So we did it from right. And then we do it from left. We get the transpose picture, and we do it iteratively until we get one block here. Right. So here the thing to observe is that what we do is basically we decompose these virtual degrees of freedoms into blocks. So this virtual vector space V is decomposed into these vector spaces, and right. So this is a general thing. You can do this for any MPS, but now we want to impose this unitarity condition, and we want to understand more structure about this this decomposition. Right. And this okay. So we basically have here n blocks. We have the top block and other diagonal blocks, and all these other diagonal blocks, they look like this big block, except the first one. And this has to be so because otherwise we would get contributions to this contraction. And since we impose that it has to be identity for all system sizes, we should only get one contribution from one block. If we get two contributions from different blocks, let's say we get 1/2 to the identity tensor n, 1/2 to the identity tensor n, but then if you look at the same condition, the unitarity condition for a larger system size, this normalization would give us 1/√2 to the m times identity plus 1/√2 to the m times identity tensor n. So it wouldn't be 1 times identity, but it would be some scalar times identity. That's why we have to have only one block that will give us contribution. And this one block has to be one-dimensional, simply because otherwise it's this MPS, if we see this as an MPS, it wouldn't be a product state. There would be entanglement between different parts. So this is the general form that we get by just imposing the unitarity of this matrix product operator for all system sizes after some constant C. So the important thing here to observe is the following. So if we approach this TJK is an operator, and basically I see this as an operator on the physical leg, depending on what type of vectors that you have on the right, virtual degrees of freedoms, and left virtual degrees of freedoms. And here what we see is that imposing unitarity, we saw that this has to be identity, and there's only this vector space is one-dimensional. So it's from Vn to Vn. Whenever you see Vn to Vn here, it's an identity in the middle. And we can have other operators in other blocks, but they won't be important when we block them. But otherwise, if you hit by an even numbered vector space on the right, you will get V2I. And the decomposition of V2I is always numbered by orthogonal subspaces where this index is increasing. So from right to left, this number actually increases. It basically means that if you if you hit with this matrix by a go up from V2I. So it can go to V2I plus 1, V2I plus 2, and so on. So basically, when you apply this matrix, you go up. You go up to this block, from right and from the left. Then we can understand what happens when we block these tensors, these local tensors. What's going to happen is that these trivial blocks will go to 0. Will go to 0 matrices because they look like this, but except this block. So this block has to be 0 for these trivial blocks. And if you multiply them for finitely many times, you will go up. If you start from bottom, you will go up. Even if you also start from here, you go up. But at the end, you will end up with 0. So these blocks will become trivial. So if you hit with this matrix with an even numbered vector, you will go to an odd numbered vector, and vice versa. Is move to this Vn. By observing what we proved are two properties. So if you block these tensors, if you look at this expression, this is actually equal to right-hand side where this is separated from this. And here R and L are the right and left eigenvectors of the CP map. So ideally, we could here put this vector that lives in Vn. Because as I told, after blocking, everything basically moves to this block. But in the future, we will use some properties. Well, we will need these guys to be positive. And that's why we are using right and left eigenvectors. And we can prove that right and left eigenvectors are actually linear superposition of Vn and even vectors for right, Vn and odd vectors for the left eigenvector. So instead of using Vn's, we can also use right and left eigenvectors. And we also show that this isometry property holds if we have M tilde and M tilde dagger hit by L and R from left and right, we get identity in the middle. Okay, so So assuming unitarity for matrix product unitary, for MPOs, we get these fixed point conditions. These are the conditions that they have to satisfy after blocking. Okay, let me also, okay. So here we can also prove one more property that I call pulling through. By using separation and isometry, we can use that we can prove that we can pull this left eigenvector from the very left to the middle and having identity here. Well, how do we do it? We basically use first the separation property and then the isometry. So this separates. And then by using isometry, we have identity here. So we can pull these left and right eigenvectors from left to right and right to left. Okay, so right. Yes, unfortunately, I should have optimized this. Yeah. Okay, so, but at least, yeah, if you trust me that this, imposing unitarity implies these fixed point conditions, then the rest will actually go through. So now let's prove that these MPUOs are actually locality preserving. So we conjugate a k-local operator by O and O dagger, by thinking that it's like a time evolution. Using separation, we know that the very left part and the left part and the right part of this is separated from the middle. And by using isometry, we know that these are identities. So basically, a k-local operator becomes a k plus 2 local operator. So there is a slide cone. Right. So if we assume MPUO property, by using fixed point equations, we basically proved that they have to be all locality preserving. Now we also go on and try to define an index. So this is the index that we define from the local tensor M. This is actually after blocking. So if you compute it for the initial local MPO M, you will get a result. So you have to compute it after blocking finitely many times. It's basically you see this M as a matrix from these two legs to these two legs, and you look at the rank of this SVD versus you look at the rank of SVD of M, but now in this direction. So seeing this as a matrix from these two legs to these two legs. This is actually equivalent to GMVW index for MPUOs. What they do is similar in that split. So they have a two-body operator. Well, they have an n-body operator, but they evolve this n-body operator. They evolve the algebra of operators supported on two sides by this quantum cellular automata, this unitary operator O, and then they have algebra of operators supported on the left and also on the right. And what they do is that they evolve the left part of it, and now this spreads. So some of it overlaps with the right part, versus they evolve the right part, and some of it actually spreads to the left. And this eta is like let's say, it measures how much overlap that we have with the support of right algebra after evolving left algebra, and vice versa. So the ratio of this is what they define as their index. So it somehow intuitively it measures how much you begin with an operator and how much of it flows to right, how much of it flows to left. Okay, so yeah, what is an index? This is the general slide. Basically, our goal is to classify objects of interest under some operation, let's call it composition. So I is a map from these objects to a target space such that we have this composition property. So when we compose two of these objects and calculate the index, it should correspond to multiplying it in the target space. I01 times I. This multiplication is in target space. And ideally, what we want to understand is that maybe there's an equivalence relation between these objects, and then we would call that this index classifies these objects under this equivalence relation. So we desire to find this kind of property. So these indices of two operators are equal to each other as long as they are equivalent under this equivalence relation. In this case, our objects are matrix product unitary operators, and the composition is multiplication and tensor product of them. And we will find out that this equivalence relation is finite at local unitary circuits. And we have this multiplication property, and that's what we are also going to find with our ratio index. Right, this is the proof. So eventually, we want to prove that if we calculate the rank ratio index after multiplying M1 and M2, it has to be equal to the multiplication of rank ratio indices calculated separately. Right? This homomorphism property. So this is the first MPO, this is the second MPO. When we multiply them, the index of this, or the rank here, is equal to rank of the multiplication of the rank of individual MPOs, and the same for the rank of the left SVD. And since our index is the ratio of these two, it gets multiplied. Right, it's blinking. So here, basically, we use very simple tricks, and we use the fixed point conditions. So the eigenspectrum of this singular value decomposition is equal to the square root of eigenspectrum of this singular value decomposition. So this, let's say this is x, This is x dagger, and the spectrum is square root of this. And now what we do is that we basically decompose two MPUOs, and then we use this trick to get this equation. And then here we use pulling through. We can pull this guy, this right eigenvector, to here, and we get this. Now we could actually take everything back. We can go from right to left here for this object. We obtain this. Then we use this relationship again, but now in the other way. So we get the square root of the spectrum. Now we use again pulling through to pull this through this leg, and then we obtain this. Now we take it back again, and we find that the eigenspectrum of this matrix is equal to the eigenspectrum of this matrix. So the important thing here is that we made use of this trick and the pulling through conditions to prove that the rank, well, the eigenspectrum here, the eigenspectrum of this big matrix is equal to the multiplication of the eigenspectrum of this guy and this guy, the product of eigenspectrum of this individual MPUO and this individual MPUO. This basically proves that the rank of multiplied MPUOs, this left to right rank, is equal to the product of rank of individual MPUOs. And this actually proves this property. So let's, so what we proved here is that with the rank ratio index, we have the homomorphism property. But we also wanted to show that it's equal to the square root of GMVW index. And that's also what we do in the paper. So you guys should go back because I'm out of time. We can also that this index is stable under blocking because that's what we desire, right? If you calculate the index for 2 sides, and then if you calculate it for 4 sides, if you have different results, then this is actually not a universal property of the MPUO that we have. And again, with similar tricks, we also prove that it's stable under blocking. And this slide shows that I'm at the end. It's great. Yeah, so what we showed is that these MPUOs are one-to-one correspondent to 1D locality preserving unitaries. We also showed the one-to-one relation of R index with GMVW index only for MPUOs. And as Fernando pointed out, like we could also use unitarity, but only for some certain system sizes. But in that case, we found that they are not locality preserving anymore. And some outlooks. Well, if I could actually light the any motivation in your heart with this talk, you can go and try to look at 2D tensor network unitary operators. Yeah. This is why like everyone spends their time here, and then I do the other things. Yes, and this is related to higher dimensional flow case systems. And one should also look at the fermionic versions of these MPUOs. I don't know what's the fermionic QTA, or I don't even know a definition. Maybe one can actually define it. Yeah. That's the end of the torture, I guess. Thanks a lot.